Let us look at a very interesting concept of gamma function. For n in all positive real numbers, gamma of n is equal to the integral 0 to infinity of x to the power of n minus 1 times e to the power of minus x dx. So that means it is defined for all positive reals. But when we look at only integers, positive integers, for n in the set of positive integers, gamma of n is equal to n minus 1 factorial. So when we restrict the domain to positive integers, this integral maps to factorials. So let's look at some important ideas behind this. One is the recurrence relation. So we start with the definition. Gamma of n is equal to the integral 0 to infinity of x to the power of n minus 1 times e to the power of minus x dx. We take n as n plus 1. So gamma of n plus 1 is equal to integral from 0 to infinity of x to the power of n minus 1 plus 1 times e to the power of minus x dx, which simplifies to integral from 0 to infinity of x to the power of n times e to the power of minus x dx. By the way, this is the integral we had seen as our last example in reduction formula method. Okay, now let's evaluate this integral using substitution method. So u is equal to x to the power of n, dv is equal to e to the power of minus x dx. du is equal to nx to the power of n minus 1 dx, and v is equal to minus e to the power of minus x. So we have gamma of n plus 1 is equal to uv, u is x to the power of n, v is minus 1 by e to the power of x from 0 to infinity. Plus, actually, as part of the formula, we have minus integral from 0 to infinity of v du. V is minus e to the power of minus x. But that minus comes out and we already have a minus here, so it becomes plus. Then du. Du is nx to the power of n minus 1. N being a constant, we take it out. Now here, the first term, if we look at it, becomes 0. So that means it disappears and we are left with the second term alone. But this term is nothing but what we had started off with, that is gamma of n. So we have gamma of n plus 1 is equal to n times gamma of n. Now remember, I mentioned this integral we had seen before, and we had arrived at that time as this is equal to n factorial. So that is our next step. But we talk in terms of gamma. Gamma of n plus 1 is equal to n factorial. So let's see how to evaluate this. Using this identity, gamma of n plus 1 is equal to n times gamma of n. Now, to evaluate gamma of n plus 1, we require gamma of n. So gamma of n is equal to n minus 1 times gamma of n minus 1. But now we require gamma of n minus 1. So gamma of n minus 1 is equal to n minus 2 times gamma of n minus 2. And so on. Till when? Till we reach 3, 2, 1 times gamma of 1. Initial factors, they all end up being n factorial. So we have gamma of n plus 1 is equal to n factorial times gamma of 1. So now let's evaluate gamma of 1 using the integral. So gamma of 1 is equal to integral from 0 to infinity of x to the power of 1 minus 1 times e to the power of minus x dx, which is equal to integral from 0 to infinity of, this becomes 1, so e to the power of minus x dx, which is equal to minus e to the power of minus x from 0 to infinity. and evaluating it, we get gamma of 1 is equal to 1. So now that we know gamma of 1 is equal to 1, let's substitute it back. We get gamma of n plus 1 is equal to n factorial. Now what about gamma of 0? Gamma of 0 is equal to, again plug it into the integral 0 to infinity of x to the power of 0 minus 1 times e to the power of minus x dx. We get integral from 0 to infinity of x to the power of minus 1 or 1 by x times 1 by e to the power of x or e to the power of minus x dx. And this, when we evaluate, we get gamma of 0 is equal to infinity. We saw gamma of n plus 1 is equal to n times gamma of n. We have seen gamma of n plus 1 is equal to n factorial. We have seen gamma of 0 is equal to infinity. And we have seen gamma of 1 is equal to 1. So I think we have laid a foundation for our next session. If you like this session, please don't hesitate to like, share, and subscribe. Questions, suggestions, and comments are always welcome. Thanks for watching. See you in the next session. That's it for now.